This is great. What a man. Thanks for being so generous and hosting me. And the pizza's pretty good. I'm from New Haven, so it's I have a high bar, but it's passable. The Hawaiian actually, it's pretty good. This is queuing theory on a cocktail napkin. I actually have cocktail napkin souvenirs where I've written my 3 main points. Grab one later. Tell your friends. And I'm going to tell you about queuing theory. I'm Dan Slimmon, and previously I've been an SRE, sysadmin type person since 2007. And previously I worked at Etsy, HashiCorp. Currently I work at a company called Clerk, which is a user management platform that integrates with React.js, really, really slick. Check it out. And that's my blog. Sometimes I blog about queuing theory. Sometimes I blog about other stuff. It's all pretty nerdy technicals. Check it out. It's on the queuing theory cocktail napkins. So in about 2013, I get up and I start driving to work, and I'm on I-95, and I'm sitting there in traffic for like 25 minutes, just waiting for the cars ahead of me to move ahead. And I finally get to my office, and I press the elevator button, and then I'm just standing there while the elevator goes ding, 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 comes back down, waiting for the elevator. Finally get to my desk, and I start pulling tickets off the Jira queue, right? In the backlog, take all these tickets that have been waiting in the Jira backlog, and now I'm working on them. I got a PR ready to go. It's waiting for CI. It's waiting for approval. So I get another one going. Now I've got 2 PRs waiting for CI, waiting for approval. So I'm like, all right, well, that's pretty good for the first couple hours of the day. I'm going to go get a coffee. And what do I do at the coffee shop? I wait in line. There's 6 people ahead of me at the coffee shop. And meanwhile, I'm thinking, boy, I sure do a lot of waiting in my life. I should really learn something about this so I can appreciate all these systems that I take part in every day that involve waiting. So when I got back to my desk, I ordered this on Amazon, expensed it on Etsy's dime. It was a good purchase. And I learned about this handsome Dane, Agner Erlang, who invented queuing theory in 1909. He was using statistical modeling. He was using statistics to study telephone networks and try to design, really efficient telephone networks where there's resources that are in use by multiple people calling, and you never know who's going to start calling when, how long their calls are going to last. So he used probability theory to figure out how to design these things. And what he discovered is so applicable to anything because it's math. It's applicable to anything that you can call a queuing system, which we'll talk about what a queuing system is. So a queuing system has 5 characteristics. If you have these 5 characteristics, then no matter what other characteristics you have or what you're made of or what you're doing, you're a queuing system. And they are: 1, some number of servers, so some number of processors where customers can be processed. Think that the checkout aisle at the supermarket is an example of one of these servers. Number 2, you got to have a certain number of spots in a queue for people to wait. It's okay if the queue is 0, then you just have a 0-size queue. You're still a queuing system. Number 3, you have some sort of queuing discipline, which just means how jobs are removed, how jobs are taken out of the queue when a resource becomes available. Is it first in, first out? Is it last in, first out? Is it a triage nurse comes and sees everybody and decides what order they come out in? That's their queuing discipline. You have a service time distribution. So this is the distribution of how long it takes to serve requests once they leave the queue and start getting processed. So maybe for a web app, your service time distribution might be, well, sometimes it takes 10 milliseconds, sometimes it takes 50, sometimes it takes 250 milliseconds, and you draw from some distribution randomly. And then finally, you have an arrival process. So this describes how customers arrive at the system and what they do when they get there. What's the average time between their arrivals and when they arrive? Do they immediately go into the queue? Which queue do they go into? That sort of thing is is your arrival process. Yes, you have a question? It does not need to be a bounded queue. The queue can be, in principle, the queue can be infinitely large. Of course, as software developers, we know there's no such thing as an infinitely large queue, and we'll talk about that. So that's a queuing system. If you have those 5 things, you're a queuing system. It's just math. And so now let's talk about how general that is, right? You've got human systems, all these telephone exchanges, the DMV. Even though when you get to the DMV, you wait in one line and they give you a letter, and you wait in another line, but you're not really in a line. Doesn't matter. It's a queuing system anyway. Then you got software systems, okay, which I would argue are just a special case of human systems. We can argue about that if you want. But CPU scheduler, I/O scheduler, they all have queues. If only one person can write to disk at the same time, then the other ones have to wait in a queue. And then as soon as you start connecting software systems to each other, now you have a distributed software system, and these are just queues all the way down. If you've got a background job processor somewhere in your stack, that's a queuing system. If you've got a load balancer that holds on to requests until a server is free to handle a request, that's a queuing system. And sometimes people don't think about it this way, but if you got a database and you have a bunch of queries that need to alter the same row, then all the queries after the first one have to wait. And where do they wait? A queue. So queuing systems are really everywhere in your life, and it behooves you to know some important things about queuing systems. I'm going to tell you 3 of those things. Since we don't have time to study all of queuing theory tonight, I really boiled it down. Hopefully these things can really stick in your head and make you think about things in a different way. So number 1 is the least quantitative but most important thing that I want to impart to you tonight, which is a queue is not a dam. It's the waterfall. What the hell does that mean? That means queuing systems are not just a piece of engineering artifice that we put in somewhere where we're like, oh, I need a queue in here. Let me just put a queuing system in here in this piece of code. Now everything can just wait in there. Queues emerge spontaneously. They're a natural phenomenon that occurs whenever more people want to use a thing than can simultaneously use it, right? And for those of us who are responsible for running a web service, that means if you have more customers trying to request pages from your web service than your whole system as a whole can simultaneously handle, queues are going to pop up. And usually multiple queues are going to pop up in multiple different places, sometimes where you expect them to and sometimes where you don't expect them to. And sometimes, through various acts of engineering, we can decide where the queue is going to form and what it's going to look like and what it's going to do when it forms. And sometimes we can even externalize the queue entirely from our system so we don't have to worry about it, so it's somewhere else. But we can't eliminate it, because as long as the conditions of queue formation are met, that more people want to use the thing than can use it at the same time, you're going to have a queue. And a corollary to this observation is if you don't make a queue, the system will make a queue for you. And generally, you're not going to like how it does that. The system will sort of deform to take on strain. You'll have out-of-memory crashes, timeouts, bizarre long database transactions. I got a good story about this if you want to talk to me later about a weird metastable failure mode with feedback loops that was a queuing thing that I dealt with just last week. And you may say, but aha, I'll simply not allow requests to enter my system when it's too busy to handle them all at the same time by sending them a 429 response, and the user can retry it later once the space is available. But the conditions for queue formation are still met, right? You still have more people who want to use the thing than can do it simultaneously. So there will still be a queue. And do you know what form the queue will take? The queue will look like angry users hitting refresh on their browser until they can load your page. Right? If you could count how many users are doing this accurately and plot that number, all the rules of queuing theory would still apply to it. It's a queue. All right, so that my point here is that you can't eliminate queues. You can play a shell game with them at best, and that's because a queue is not a dam. It's the waterfall. All right, number 2, L equals lambda W. Got it? L equals lambda W. All right. Well, maybe we'll talk a little about that one a little more. Okay, so this is Little's law. And Little's law states a relationship between long-term average properties of a queuing system in a stable state. So the 3 quantities in question here are the average number of customers in the system, including those in queues and those actively being processed. All the customers together, how many are there on average? Lambda is the average arrival rate. So how many customers are arriving per unit time. And W is the average amount of time that each customer, if you measure from end to end, for the time they arrive to the time they finish getting processed, how long they're waiting. Okay? This is always true. This is breathtakingly general. It doesn't matter what your queuing discipline is. It doesn't matter what your arrival process is. It doesn't matter what you do with the, nothing matters other than you have a queuing system and it's in a steady state and you're looking at the average numbers. So it applies to any of those things I showed you before, the human systems, the software systems, the distributed software systems. It's always true. It doesn't matter whether a customer is a Jira ticket or a car or a web request or a network packet or an insert query. It just always works. And we'll have an example of Little's law a little bit later. But first I want to tell you about point number three, which is that queues have 2 basic states, empty and full. I'm being a little imprecise there, but I really kind of mean that. And I'll tell you what I mean more precisely. So if you have a queuing system in some sort of steady state, it has some average utilization of the processors. So say 50% utilization means that the CPU is doing something 50% of the time, and the other 50% of the time it's idle. If you have 75% utilization, you have more average customers in the queue, right? You move along this line. As you approach 100% utilization, you approach infinity customers. Okay? Infinity. This is asymptotic. All right? And if you even get close to 100%, then you get close to infinity customers. And that may seem counterintuitive, so let me have a little demo. So we want to talk about queuing systems with 100% utilization, right? This is a queuing system that is in the 0 customer state. If a queuing system is ever in this state, it can't have 100% utilization because there's no utilization right now, right? So in order for there to be utilization, we have to add a customer. Now this customer is being processed, okay? So if we stay in this state forever, great, we have 100% utilization. But we can't control how long it takes for the jobs to finish or when customers will arrive. So eventually we're going to transition back out of this state randomly back into the 0 utilization state, which we already said is not allowed. Okay? So therefore, this state's not allowed. We're not ever allowed to be in this state. And now we're not ever allowed to be in this state either, because this state can transition into the state we're not allowed to be in. So this one's not allowed. Okay, but what if we had another customer to fill in the spot when this one finishes? Well, great. Now this one, oh no, we're back in the 1 customer state, which we already said was not allowed, right? If we want 100% utilization, we have to keep adding customers so that we never have any idle time, and then we have infinity customers, okay? This is very real, and there are many real-world examples of this. And since we know little, so this is what I mean by a queue is either empty or full. Roughly somewhere, there's a line somewhere around here where if you're running more than that utilization, you're going to be having a bad time. And also, since we know Little's law, it's not just the occupancy, it's not just the number of customers that approaches infinity, it's the latency too. The average latency of all the jobs going through the system are going to track that occupancy number. They're proportional. You ever logged into a server that had 100% CPU utilization for a long time? You know what the load average was? I've seen it get up to thousands, right? If you've ever worked at a bar and the register was busy for a long time, somebody was always checking people out at the register, well, the line was out the door, right? This is just how queues work every time. All right, so I got some examples to try to drive some of this stuff home and show you how I use it in my day-to-day. Suppose you have this system here that has an average, it's a web service, has an average latency of 60 milliseconds and an average throughput of 2,000 requests per second. Now, using Little's law, we can answer the question, how many concurrent requests does this service have on average? We just know this from Little's law. We don't have to know anything else. We don't have to graph that number. We just know it because L equals lambda W. Lambda is 2 requests per millisecond. W is 60 milliseconds. So the average concurrency on this service is going to be 120 requests in flight. It's going to vary around that number, but that's going to be the average. And this has very real impact on how much memory your boxes need, how many file handles, all this stuff. And it helps you make some scaling predictions too. So for example, if we have 10 web servers and a load balancer in front of them for this service, how many concurrent requests per web server will there be on average? There'll be 10, 12, 12. There'll be 12. And it doesn't matter if you're like bucket filling the backend. It doesn't matter what you're using, round robin or randomly distributing the requests or what. The average is going to be 12 in-flight requests per server. Okay. What's going to be the average concurrency if you had half as many containers? Well, you're dividing one side of the equation by 2, so you're dividing the other half of the equation by 2, or multiplying the other variable, right? One goes up, one goes down, so you're going to have 24 requests per container on average. What if you made the requests 50% faster? You're going to have half as many, right? You can make all these scaling judgments without knowing anything. Notice I haven't told you what framework this is using, what programming language, who the customers are, what it does. None of that matters if you have a queuing theory understanding of it for these calculations. And that's why it's so useful. I can, as a reliability person, as a software reliability person, I can very often understand what the problem is with a system somebody shoves in front of my face by making calculations like these without even needing to ask them very many questions about what read very much code or ask very many questions about what the software does. Another example. This is in Postgres, a graph I saw the other day in my job where this is the number of processes that are waiting to write to what's called the write-ahead log, which is a synchronous write. And only one process can write to it at a time. And I started to see spikes. I was like, oh, why is this? Normally it's down here between like 0 and 10, but sometimes it spikes up to 200. That's probably not right. I should figure out what's going on there. That means that something is being utilized 100%. That mutex that controls the write-ahead log is being utilized 100%, and the queue is blowing up. Right? And in fact, that we know that since the size of the queue didn't grow without bound here, right? It's stuck at 200 and stayed there for 2 observations in a row. Well, we know that if something's 100% utilized, the queue is going to grow without bound. So this allowed me to be like, all right, well, I better figure out where the other processes are piling up, right? The queue's piling up somewhere. It stopped piling up here. So then you start going around like, okay, well, where are they now? Are we dropping the request? Are we throwing errors? Are we using a ton of memory somewhere else? So without queuing theory, this is just sort of a quirk of your database. Sometimes it spikes like that. I don't know. I got shit to do. if with queuing theory, this is very clearly a distributed system bottleneck that you better solve soon, or these spikes are going to show up elsewhere in your system and you're going to have real big problems. So my point here is not that everybody needs to grab a queuing theory textbook and work through the probability theory. If you can't, you should if you want to. But we don't need to all be sending LaTeX documents to each other. And my point is that having queuing theory in your head is immensely useful because it lets you reason about the behavior of software systems without understanding all of their details and reading all of their code. It's an incredibly effective theory. But it takes a while. It takes some repetition. You got to use these ideas a few times in a row before they start to click. So what can you do tomorrow when you get back to work with this stuff that will help it click as you go through the rest of your life? And the main thing that I would suggest you do is create a dashboard like this, which I've had at all my jobs since college, the saturation dashboard. Basically, think of everything, find every metric in your system that represents things waiting in a queue, no matter what kind of queue or what form they take, anything that's being queued, graph it on here. And now look at this dashboard every so often. I look at mine every day. I try to look at it on different time scales. And so this one has like load balancer pending requests, load average on web servers, the IO queue depth on your database server. These are all saturations of queues. And if you can find patterns in here on this, if you're scrolling down this dashboard and you find a pattern, you're like, I'm going to try to explain that. And you find that you can't explain it, then you've found probably a serious distributed systems problem, and you should look into that thing. Sometimes it'll be a rabbit hole that wasn't worth going down, but you'll have learned more about your system's behavior, and you can rule that one out next time. And I bet the next one will be worse. So try making this dashboard. I think you'll learn a lot about your system's behavior, and it'll be and then you'll get this stuff in your head. It'll become part of what you do. So if you're intrigued, I have got a few links to my blog posts about queuing theory up on here, blog.danslimmon.com/DC systems. There's a little list there. And that's my email address. Email me anytime. I'm happy to love talking about this stuff. So let's do it. And I appreciate you inviting me to give this talk. May your queues always be empty. Thank you. Yes, please.
If queues in general can only have two states, how do you optimize between having an empty queue, which is great for user experience but terrible for server efficiency, and having a full queue, which is the opposite?
You cannot optimize for both of those things at the same time. If you want fastest possible throughput, you have to sacrifice your fastest possible latency. And if you want fastest possible latency, you have to sacrifice your peak throughput. There's really no way around it. You need to build two separate stacks if you have customers that have both of those problems, if you want to solve both of those problems at the same time. Oh, microphone.
Hey. Nice. So you hinted that there's a lot of depth in this area. You know, that we could probably throw out a huge number of words about particulars in queuing theory. You highlighted, as you said, Cree. Do you feel like that's really like the cream of the crop, or you get a lot of benefit from getting the top 15 items?
From reading the textbook, sorry, that was on the microphone. Good. So I got a lot out of it. I have a math background from college, and I found it very interesting to do the math. These three things are really like the main ones that when I sat down to write this talk, these are really the three ones that floated to the top. And I think once you get the hang of using these three ideas in your day-to-day life, the rest of it sort of flows naturally. I rarely find myself looking up particular theorems or whatever, because this stuff solves. It's like the 80% of the 20% of the stuff that solves 80% of the problems. Yeah.
Thanks for the awesome talk. I'm curious how you map good put to these sorts of problems, because like throughput in some systems can mean nothing. I can return abort to the user as like very quickly, low latency, send throughput through the roof. So how do you map good put to these problems, or is it just a matter of just only reasoning about measuring that metric? Is it more of a measurement problem?
You can, sorry, I was getting, this was an incident call for my work. I'm going to ignore that. So you, queuing systems are surprisingly decomposable, and there are a lot of situations where you can decompose the good put and the total throughput, or the rest of it, as and think of them as separate queuing systems. If you want to think of it all, you can think of it all together, where the latency distribution includes both the errors that return after 0 milliseconds and the super long requests that return 200 after 20 seconds or whatever. Think of it all as that one distribution. But you can also, with caveats, it's often worthwhile to decompose the system into different requests that are different types of requests that are flowing through the system, and treat them as having separate distributions. Does that make sense?
If that's all questions, thank you so much.